Hello everyone, in today's video we will be going through our first reacting design example. So let's go ahead and read the problem statement. Feel free to pause the video at any time and try to solve the example yourself, and then you can compare your solution with mine. So let's go ahead and start. A first order liquid phase reaction of A gives you 2B is to be carried out in an isothermal and well mixed batch reactor. The rate of reaction of A is given by Ra equals negative KCA with the K value of 1 per hour. If the initial concentration of A before the reaction is 15 moles per liter, calculate the concentration of A after 120 minutes. So what I like to do before I start solving the example is identify the type of reactor we're working with and write down all our givens. So as stated in the problem statement, we're working with a batch reactor. Okay. Isothermal basically means that the temperature is constant in the reactor, which basically means that the reaction rate constant is constant because the reaction rate constant K is a function of temperature. It depends on temperature. So if the temperature is constant, then the K is also constant. Okay. Well mixed basically means that the concentration at any point of the reactor is the same at a certain time. So for example, at time equals 0, the concentration anywhere in the reactor is the same, and at time equals, let's say, 20 minutes, the concentration at that time anywhere in the reactor is the same. So that's what well mixed basically means. Let's start writing down our givens. Okay. Well, first we know that the reaction is A gives you 2B. Rate of reaction equals negative K Ca. K has a value of 1 per hour. Initial concentration equals 50 moles per liter. And what they're looking for is the final concentration at time 120 minutes. Okay, so let's go ahead and start with our mole balance or material balance. Input minus output plus generation. In case there was a consumption, it will be minus consumption. Okay. Equals accumulation. Now, since there's no input or output, these two terms will be 0. We'll be left with generation equals accumulation. And from the previous video, we know that generation equals rate of reaction times volume. Accumulation equals the change in moles over the change in time. We'll go ahead and sub these two terms into our original equation, which will leave us with RAV equals change in moles over change in time, differential time. Okay. We already know that we need to change this in terms of concentration because the rate of reaction is in terms of concentration, and we're looking for the final concentration. So let's go ahead and do that. Sub in our rate of reaction, and change the Na in terms of Ca. So our rate of reaction is negative K times Ca times V equals, we know that Ca concentration equals moles over volume. Therefore, as discussed in our previous video, Na equals CAV. Okay, so differential CAV over change in time. Now, since the volume is constant, it can be taken outside of the differential, which will be something like this: V dCA over dt, and the left side will stay the same, negative KCA times V. The volumes can cancel from both sides. We'll be left with negative K Ca equals dCA over dt. Now we'll rearrange this equation. We'll move the dt to this side and the Ca to that side, and it'll look something like this: negative K dt equals 1 over Ca dCA. Okay, sorry, I'm going a little fast here. If you have any problem, please leave it on the comment section, or review the batch reactor theory. It will clear anything you missed out here. So we'll differentiate both sides. We'll integrate both sides. Sorry. So here the limits are from 0 to time, to the final time. Here from the initial concentration, the limits are from the initial concentration to the final concentration. The left side will be negative K times time equals ln Ca over Ca naught. Okay, we went through this in the batch reactor theory and the math review. So if you have any problems, check those two videos out. So we're solving for Ca. In order to get rid of this ln, we need to make both sides to the power of E. Now that's cancelled. We'll be left with Ca over Ca naught equals E to the power of negative K times T. Isolating for Ca as a function of time equals Ca naught times E to the power of K times T. That is our equation. Now, to copy and paste our givens, okay, let's copy and paste this, copy, come on, paste. It's much faster than rewriting it all over again. So what is he looking for? He's looking for the final concentration at this amount of time. Now we need to respect the units. Since K is given in hours, our time must be also in hours, so let's go ahead and convert that. Time equals 120 minutes, and what we want it to be in is in hours. Okay, so 1 hour has 60 minutes. Minutes and minutes will cancel, and we'll be left with hours, and that will be 2 hours. Time equals 2 hours. So let's go ahead and sub in our givens. So we want Ca, the concentration of A at time of 2 hours, which equals to, our Ca naught is 50 moles per liter, times E to the power of negative K, which is 1 per hour, times the time, which is 2 hours. Okay, which makes sense. Keep in mind the unit conversion. Check if the final answer will give you the correct units. You can see that hour and hour here are cancelled, and you'll be left with moles per liter. So let's go ahead and do that. 50 moles times e to the power of -2 will give you 2.03. So Ca equals 2.03 moles per liter, which makes sense because A is a reactant. So if we plot the concentration of A inside the reactor versus time, concentration of A versus time, we'll notice that at time 0, the concentration is very high because it hasn't reacted yet. And as time goes on, we'll notice a slight decrease in the concentration until it reaches close to 0. In the contrary, we'll notice that the concentration of B, which is the product, B, versus when we plot it versus time, the concentration of B versus time, we'll notice that at time 0, the concentration of B is 0 because it's a product. There's no product being generated yet. But as time goes on, we'll notice an increase in the concentration of B until the reaction stops, and then there's no more concentration of B produced. So your answer does make sense. Our answer does make sense, and that's it for today's example, and we'll do another example on the batch reactor. And until then, bye bye.